each of these examples, for now, don't worry about the shear force diagram, just calculate the reaction forces using moments at each of these supports. What's the reaction force at A? So if we label this A, what's the reaction force at B? So we'll label this B. I could just point this out to you. If we look at this example, the uniformly distributed load, 2 kilonewtons per meter. So that means the force that this beam is exerting is a force of 2 kilonewtons for every meter of length. So if I want to find the total resultant of that force, I multiply, so the resultant equals the 2 kilonewtons per meter rather, multiplied by the length of the UDL, which in this case is 8 meters. So I'm going to get 2/8 as 16 kilonewtons acting downwards, and this is going to be acting, in this case, in the middle of the beam, because the UDL is across the full length of the beam. So in the middle, I've got a reaction force of 16 kilonewtons. So now I treat the problem as a point load of 16 kilonewtons acting down. So if we look at question number 3, anticipating the next question, when you get to that, you'll see that this time you have a UDL that's from the 5 meter mark to the 20 meter mark. So now you've got a point source of 8 kilonewtons acting down, but also a UDL of 2 kilonewtons per meter acting down. So what I would then do is I'd find the resultant and assume that's acting in the middle of the UDL, which is from there to there. Okay? So 2 kilonewtons again multiplied by the distance will give you the size of that force. When you get to the next page, we'll look at these, but think about what effect this has. Look, the fact that the beam is pivoted not at the end but here, what effect will this have when I take the pivot? Just think about clockwise and anti-clockwise. If this was acting on its own, would it be acting clockwise or anti-clockwise around that pivot? Or that pivot, whichever one you take.